Hello everyone, welcome to today's class. The topic that we are going to see today is traditional symmetric key ciphers part 2. So the first topic that we are going to begin with is the polyalphabetic ciphers. So what is polyalphabetic cipher? Now in polyalphabetic substitution, each occurrence of a character may have a different substitute. So here the relationship between a character in the plain text to a character in the cipher text is one to many. So for example, A could be enciphered as D in the beginning of the text, but as N at the middle. So to create a polyalphabetic cipher, we need to make each ciphertext character dependent on both the corresponding plaintext character and the position of the plaintext character in the message. So this implies that our key should be a stream of subkeys, in which each subkey depends somehow on the position of the plaintext character that uses that subkey for encipherment. So the first polyalphabetic cipher that we are going to see is the Autokey cipher. So this is a polyalphabetic cipher where the subkeys are automatically created from the plaintext cipher characters during the encryption process. So the first subkey in this Autokey cipher is a predetermined value, which is secretly agreed upon by the sender and receiver. So here you can see in this diagram that I have a plain text, okay, which is attack is today. And here I have the corresponding p value, okay, which for A it is 0, for T it is 19, for A again it is 0, for C it is 02, K 10, and so on, okay. Now here the key stream that we will be seeing, the first sub key, okay, it is secretly agreed upon by the sender and receiver. So say we have Alice, okay, and we have Bob. The first sub key should be agreed upon by them, okay, and they have selected 12, okay. Now the second sub key is the value of the first plaintext character. So the second sub key, which is this one, is the value of the first plaintext character, right? Okay, then the third sub key is the value of the second plaintext character. So the third sub key, this is our third sub key, and the third sub key is the value of the second plaintext character. So it will go on, okay. As you can see, this will go on. So this is how the key stream is usually generated. Now if we want to make the ciphertext from this key stream and p value, what we do is we just basically do this Caesar cipher, which is C equals to p plus k mod by 26, right? So if you add 0 with 12 and mod it with 26, you will get 12. Similarly, 19 plus 0 mod 26, 19. So in this manner, you're going to get your ciphertext, okay? Now, what will happen in the ciphertext that is generated? You can see the generated ciphertext is MT, MT, and it goes on, like. But you need to notice something. Here you can see that there is two T's, right? But for one T, okay, in the ciphertext, the substitute is T, and again it is M. Okay, so in the plain text, a character in the plain text can have different substitute of characters in the ciphertext. So you see the character T in the plain text is T in the ciphertext, but again it is M in the ciphertext. So same goes here. You see here is a T and the substitute is L. So this is hard for cryptanalysis, okay. So attackers can't break the ciphertext, okay. So it will not be easy for them. Again, you see for the A here, you see there are how many A's? 3 A's, and for 3 A's the character here are M, T, and D. Each of the time they have a different substitute in the ciphertext. Now the cryptanalysis, so this is not affected by a single letter frequency statistical attack, but however it is vulnerable to the brute force attack. Why? Because since we are using the Caesar cipher for generating the ciphertext, so attacker can use this brute force attack or exhaustive key search method to decipher the ciphertext. Now moving on to the Playfair Cipher. So this is another polyalphabetic cipher that was used by the British Army during the World War I. So the secret key in this cipher is made up of 25 alphabet letters arranged in a 5 into 5 matrix. So here you can see there is a 5 into 5 matrix, right? So the secret key is made up of this 25 alphabet letters. Now we have 26 letters, right, in our alphabet. But here what we do is the letters I and J are considered as the same when encrypting. You see, I and J are considered as the same when encrypting. So here you can see a secret key is formed of the 25 alphabet letters, okay, and I and J are given the same priority. Now you see that we can have different arrangements of the letters in the matrix, and it can create many different secret keys. So before encrypting, if we say that two letters in a pair are the same, then we introduce a bogus letter between them to separate them, right? All right, then after inserting a bogus character, if the number of character in the plain text is odd, okay, what we do is we add or we append one extra bogus character, okay, at the end, so the total number of the characters is even. The cipher uses three rules for encryption. So Playfair Cipher mainly uses three rules for encryption. So the first rule, it is if the two letters in a pair are located in the same row of the secret key, the corresponding encrypted character for each letter is the next letter to the right in the same row, with wrapping to the beginning of the row if the plaintext letter is in the last character in the row. Then the next rule is if the two letters in a pair are located in the same column of the secret key, the corresponding encrypted character for each letter is the letter beneath it in the same column, with wrapping to the beginning of the column if the plaintext letter is the last character in the column. So if they are in the same row, then we choose the next letter to the right in the same row. And if they are in the same column, what we do, we choose the letter that is exactly beneath them. So if for same row, we choose the next letter to the right of that same row, and if it's in a column, then we choose the letter which is immediately beneath them. So if the two letters in a pair are not in the same row or column, the corresponding encrypted character for each letter is a letter that is in its own row but in the same column as the other letter. So this might not make sense to you, but let us see how this works, okay, with an example. So what we will do is we will now encrypt hello using the secret key. So this is the secret key that is given, okay, and we will encrypt the message hello. Now what we first need to do is we need to separate two letters, right? But we see that here L and L, these two are the same, so we need to separate them using a bogus character. The bogus character that we'll be using is X, okay? So when we group the letters in two character pairs, we get H, E, L, L and O, right? So since L, L are the same pairs, okay, we need to separate them using a bogus characters. So here we have separated the L using a bogus character, which is X, okay, we have used LX, and then what we need to do is we need to check if the total number is odd or even, right? So is it odd or even? So we see 1 2 3 4 5 6, so it's even, so we don't need to add any bogus character at the end, okay? So now what is happening? You see HE is converted to EC, but how? Here we have the H and E of hello. So the first rule states that if they are in the same row, then we choose the character of that same row that is to the right, right? So we have to choose the character that is to the right of them if they are in the same row. So the right character of H is E, and the right character of E is C, right? So that is why we choose for H, we choose E, and for E, we choose C. That is why it is EC. Now, can you tell me what it will be for LX? So let us see where LX is. So LX is here. It is in the same column. So we need to choose the character that is immediately beneath them. So for L, we need to choose Q, and for X, we need to choose Z. So LX will be QZ. Okay, and lastly, we have L and O. So let us see where L and O is. So L is here, okay, and O is here. So for L and O, what we need to choose is, we need to choose the character that is in the same column of the second letter, right? So since L and O are not in same row or column, we need to choose the character for L, okay, which is in the column of O. So the character of L which is in the column of O is this one, B, right? So for L we need to choose B, and then for O, what we need to choose? We need to choose the character that is in the same column as L and same row as O. So we need to choose X, okay? So we choose B and X for L and O. So for L and O, we choose B and X. So one approach that you can do is, so L and O, between L and O, what you need to do is, you need to draw this square between L and O. Now this square, okay, will give you the characters. So the character that you will find for L is B and for O is X, okay? Now for the plain text hello, the generated ciphertext that we see is EC, QZ and BX. Now let us move on to the Vigenere cipher. So this is a polyalphabetic cipher which was designed by Blaise de Vigenere, a 16th century French mathematician. This Vigenere cipher uses a different strategy to create the key stream. So the key stream is a repetition of an initial secret key stream of length m, where we have 1 less than equals to m less than equals to 26. Okay, so the key stream is a repetition of an initial secret key stream. So let us see what this is. Okay, so here we are given a key stream, okay, which is Pascal. So the initial key stream for this key Pascal is 15, 0, 18, 2, 0, 11. Okay, now we will be using this key stream, okay, this key, to encrypt our message, and we will be repeating this. So let us see how we do this. So the plain text that we are given is, she is listening. She is listening is our plain text, okay? And then what we do, we basically find out the value of the plain text, P's value, and write it down. As you can see, we have done that. Now the key stream that we are given is Pascal, okay? And Pascal generates this key stream, 15, 0, 18, 2, 0, 11. This is the representation of Pascal, right? Now you write it here firstly. After writing it down, what you will do is, you will start writing it again, okay? So after you have finished the key stream, then you will start the key stream again. After it has ended, then you will start from the beginning again. So that is what it means, a repetition of the initial key stream. After this, what you'll do is basically the Caesar or additive cipher. You will add them, that is C equals to P plus K mod 26. All right, so you will just add them up and mod it. This is how the Vigenere cipher works. Okay, so the generated ciphertext from this is this one, right? So using 18 plus 15, okay, mod and if you mod it by 26 will give you 07. So this is how you generate the ciphertext. So one thing that you need to notice here after generating the ciphertext is, say for S and S, the occurrence in our ciphertext is H and S, right? So for S, it has a different substitute in our ciphertext. Similarly, for E, it has a different substitute, W and G. So for N and N, it has a different substitute as well, N and C. So this is how the polyalphabetic Vigenere cipher works. Now let us move on to the Hill cipher. So this Hill cipher was invented by Lester Hill. So unlike the other polyalphabetic cipher, the plain text is divided into equal sized blocks. So in this Hill cipher, the key is a square matrix of size m into m, in which m is the size of the block. All right. So the plain text is of size lm, and the ciphertext will also result in a size of lm. The key that we are using in this Hill cipher needs to have a multiplicative inverse as well, okay, in order to maintain the integrity of our plain text. So if you want to visualize this, you can see if this is the ciphertext P into K, right? So here what we are doing, is the ciphertext will be in a matrix. Okay, the plain text will also be in a matrix, and the key will also be in a matrix, right? Now the size of this key is m into m, right? Similarly, the size of p will be l into m. So therefore the size of our ciphertext will be l into m. All right, and this is how the ciphertext is calculated. You see, for say this is p1 and this is c1, this is k1, right? 1, then k1 2, so goes on. So this c1, as you can see, is calculated as p1 k11, right, plus p2 k21, and it goes on. So in order to calculate this ciphertext, what we need to do is we need to multiply this entire row with this entire column. Okay, that is how you will get the c1, and so on. Now moving on to the transposition ciphers. So a transposition cipher does not substitute one symbol for another, rather it changes the location of the symbols. A symbol in the first position of the plaintext may appear in the 10th position of the ciphertext, or else a symbol in the 8th position in the plaintext may appear in the first position of the ciphertext. So in other words, a transposition cipher reorders or transposes the symbols. So in transposition cipher, what we are basically doing is we are only changing their positions, okay, in the ciphertext. So as you know that transposition cipher is of two types. So the first type is the keyless transposition cipher. So in the keyless transposition cipher, we have two methods, one of which is the zigzag method and the next is the fixed column method. So here we have a plain text, okay, meet me at the par. So in the zigzag method for our keyless transposition cipher, what we are doing is we are arranging the plain text in a zigzag manner. As you can see, MEET, MEAT, THE, PARK. So this is meet me at the park, right? So we are arranging them in a zigzag fashion, okay? Or else you can also see that the odd positions, okay, odd positions here are kept in the first row, and the even positions in of the plain text are kept in the second row. And then the ciphertext is generated by taking the first row followed by the second. So you take the first row, okay, and then you take firstly the first row and then you take the second row, okay? So in this manner you generate the ciphertext. You see here MEMA, so MEMA is here, right? MEMA is here. Then we have TEA, TEAK. So this is the first row and that is followed by the second row. So that is how we generate our ciphertext using this zigzag method. Now, moving on to the next method, which is the fixed column method. Here, what happens is the sender and the receiver will agree on the number of columns. So say, for example, the sender and the receiver agrees on 4 columns. So what will happen here is that in the column, the plain text will be set, okay? So you see, meet me at the park. So according to the 4 columns, the plain text is arranged. Then what happens in the fixed column, the ciphertext is generated column wise, okay? So you take the first column, then you take the second column, then you take the third column, and then you take the last column. So you see the first column is MMTA, so here it is MMTA. Then the second column is EEHR, then it is EEHR. So in this way the ciphertext is generated. Now moving on to the keyed transposition ciphers, what is happening in this keyed transposition cipher? We see that here we divide the plain text into groups of predetermined size called blocks. Then we use a key to permute the characters in each block separately. So here what is happening? We have a plain text, right? And this plain text is enemy attacks tonight. Now we will take a block, okay, a block size. So let us take a block size of 5. And what will happen now is we will separate the entire plain text into a size of 5 blocks, okay? So you see this is 5, 1, 2, 3, 4, 5. Again, the size of this block is 5. The size of this block is 5. So enemy attacks tonight. The size of this block is 5. In the end, if you see that there are characters which are less than the predetermined block size, then we introduce a bogus character. So we introduced a bogus character which is Z here, right? So enemy attacks tonight. Since here it would have been 4 characters only, so we introduced a bogus character. Now we have been given the key, okay, in this key transposition cipher. So this is the position of my plain text, okay, plain text, and this is the position of my cipher text. So you see here what happens is the position of my plain text 3. So here the position of my plain text, this is 3. So let me write it 1, 2, 3, 4 and 5. So the position of my plain text 3 is said to be at the position of 1 in my cipher text. So E will be in the first position of my cipher text. Then in the second position of my cipher text, the character which is in the first position will be in the second position, right? So the character which is in the first position, E, will now be in the second position, here, E. Then the character that is at the fourth position of my plain text, which is M, will be at the third position of my cipher text, here. Now, similarly, you see 5, the plain text character which is at position 5 will now be at position 4 of my ciphertext. So in 5 we have Y, right? So here we have Y, and lastly we have N, which will be here, right? So in this way you generate your ciphertext using this encryption process, okay? And then you will use decryption process in the reverse order to decrypt it. So the generated ciphertext is done here, and we have generated this by taking it row wise, right? So this ciphertext can be generated either row wise or column wise. So for now we have seen the ciphertext is generated row wise, right? Now in the example that we'll see now, here we will be seeing how the encryption and decryption process is done, and how the ciphertext is also generated column wise. So it is not mandatory that the ciphertext is generated always in row wise or column wise. You can use any approach you want. So this is the example that is given for our keyed transposition cipher. So we have the enemy attacks tonight and the block size is 5. This is our plain text and the block size is 5. So we write it row by row. So see, enemy attacks tonight, right? All right, so after arranging this, after arranging the plain text row by row, what we do is we use the key that is given. And using this key, we are now encrypting this message. So similarly to the way that I have addressed earlier, we encrypt this key by reordering their position, okay, by changing their position. So in the plain text position, which is at 3, will now be changed to position 1. The plain text position which is at 1 will be changed to 2, which is at 4 will be changed to 3, which is at 5 will be changed to 4, and which is at 2 will be changed to 5. And after doing this, this will be generated, right? So after generating this, what we will do now, we will generate the ciphertext now column wise, okay? So we will read it column by column. So you see ETTH is our first column. So here ETTH is our first column. Then we have EAKI. EAKI. So similarly, we will generate the ciphertext column by column. After Bob receives this ciphertext, Bob will read the ciphertext column by column. Okay. Now, after Bob reads this ciphertext column by column, the key that we have been given, it will be followed in the reverse order for decryption. So here you see that position 1 is this one, right? So is now this position 1 will be changed to position 3 in the plain text, right? So this E will be changed to position 3 in the plain text, okay? Then in position 2, it will be changed to position 1 in the plain text. Then for position 3, this will be changed to position 4, right? So this is changed to position 4. So similarly, Y, which is at position 4 in the ciphertext, will be changed to position 5 in the plain text. And lastly, N, which is at position 5, will be changed to position 2, right, in the plain text. So this is how you decrypt it, okay? So the key will now be used in the reverse order, and then you can have the plain text at the Bob's end. So let us see at the last topic, which is the stream versus block ciphers. So in a stream cipher, encryption and decryption are done one symbol at a time, okay? For example, in monoalphabetic ciphers, Autokey ciphers, and Vigenere ciphers, all of them are stream ciphers because encryption and decryption are done one symbol at a time. But a block cipher is a cipher where a group of plaintext symbols of size m are encrypted together, creating a group of ciphertext of the same size. So in a block cipher, a single key is used to encrypt the whole block, right? Even if the key is made up of multiple values. So for example, we have seen Playfair ciphers, Hill ciphers, and key transposition ciphers of this category. Thank you. This will be all for today. Hope you have enjoyed and understood the class.